Oh, yeah.
Freaking 12 hard drives in the thing.
All right, before I get into anything specific, any questions? Have you guys tried anything out? Any questions? We didn't really do that much the first night. Yes?
I'm adding the class.
Oh, well, that's a good statement. After class, just come back with me. We'll get out there and talk about what you missed. Okay. So I kind of want to just throw a couple of things at you and see how you react here. I gave you that one differential equation, but it was really just a check equation, right? So that's going to happen every now and again throughout the semester. We're going to have things to check, and then we're going to try to see a pattern and what worked, and then we're going to try to build a general way of solving things. So it's kind of like, in algebra, you start off with something like this, and that's damn easy as hell. And then they make it a little bit harder with, then you have to kind of work with, do a little bit of shit, but it's still kind of like you can just attack it directly. Do you know what I mean? Then they do this kind of shit to you, and when you're in algebra and you're like, oh my God, what the hell is this shit? And that wasn't, now we got to develop a new method. So the same kind of thing happens when we start talking about other kinds of equations. The equations we're going to deal with are have y in various orders of differentiation on them, and they're interrelated. So I could talk about this at several different levels. A general equation deals with how certain things interact with each other, right? A differential equation is actually more true to life because most often like rates of change interact with each other. Flow rates, in the amount of water flowing through somewhere, that's a derivative. And so it kind of more generalizes the kind of equations that happen in real life. So differential equations aren't something where you just start with something, you do derivatives, and you make some evil shit out of it. It's just observing real life. There's a rate. Oh, there's the jerk. Anybody know what the jerk is? You got... There you go. I love it, right? It's kind of like appropriate. It's like my first car.
I was going to say my ex, but...
Jerky all the time. You want to go? You want to go? You want to go? Okay, I want to go. So that's the jerk. Anyway, so you get these rates of change that interact with each other in certain ways, and then you have equations that are built from them. And then you want to figure out, well, what was the original function? What's the equation of position or whatever it is you're dealing with? So then you have to develop ways to solve those things. Some equations you can solve by observation. Sort of like that first one, x minus 2 equals 6. I mean, even pretty early in algebra, you can just solve it by looking at it. So if I put up here y prime equals y, think about it for a second. What does that mean? Say that in English. Let's see which one it was. But so this means the derivative of the function is the function itself. And of course, what is that? E to the x. Now, if you think, now be really, really careful. Is that the answer?
It's a, yeah. It is a answer.
Okay, I like it. So generalize it for me. Can somebody generalize it for me? For example, there is an answer to this that we call the trivial solution. And the trivial solution basically is when you set it equals 0 because everything's got the thing in it. Everything's got y in it. So if I let y equal 0, is this true? Yeah. Yes. Now, this doesn't represent y equals 0 currently, right? This can't be 0. That's the thing about e to the x. It's got an asymptote there. But this isn't the general solution. This isn't the way to write the entire family of solutions to this thing. What else solves this? What about 2e to the x? Does that work? Right? Yeah, of course. In fact, all right, generalize that for me. What's the idea? Yes. So the real general formula, the real general form of the solution is this. Right? And now does this contain y equals 0? Yeah. Yes. I like it. C equals 0, and you get that answer. Do you guys follow? So there's going to be, thankfully, a theorem that you start to wonder, if I solve a differential equation, what is it that tells me I got all the answers? Right? We're going to have a nice theorem that kind of helps us, and it's kind of It's one of those theorems that is really hard to break it, so it works almost all the time, unless you make a really funky function on purpose, and then it won't work for it. Yes?
So, wouldn't you have to have like a plus C kind of?
Oh, now let's see.
situation?
Think about it. If it was e to the x plus 2,
Yes.
the plus 2 would exist here, but it wouldn't over there. So it wouldn't be equal.
Gotcha.
I love it. So you gotta, now what really sucks is in 180 we pound you in the head with, you didn't put your plus C, you didn't put your plus, and you're like, plus C, everywhere. Even when you have a definite integral the first few times, you probably put plus C there just to be like, oh, I have to cover my ass. And I try to give you a little bit of warning. In diffie-q, the constants are going to be themselves something even to worry more about, and you can't generalize it like that. I know 180 kind of sets you up for that, but one real reason you could see that it's not going to work exactly the same way is in 180 you always had, at worst you had derivative of y in the function of x. I mean, now look at this. This is a derivative of y equals a function of y. You never saw something directly like this in calculus. You guys with me? Okay. So this is a different level of thing to worry about. I'm going to bring back in the idea from calculus and show you where it comes from looking at certain differential equations, the idea of plus c. There will be times when plus c will be fine. This one doesn't work. I like it. In fact, what would happen if, I think this is one of the ones I want to look at. Oh, let's kind of build up here. This is one of the ones I want to look at. Look at this one for me. What about this guy? Now, what have I done there that's different? Now we're talking about the second derivative. All right, let me think about it. I mean, it's still saying that the derivative of the function is equal to itself, because then you derive it again and it's equal to itself, or proportional to itself, right? So it's probably still an e to the x kind of thing, but it's not e to the x, because where would that 4 have come from? Twice derived. So what must have been going on? E to the 2x. And again, some of this is getting used to the possibilities. You're thinking about things in a slightly different way than you have. It's not a hugely different way. It's kind of, you know the derivatives, you just got to bring it into what this thing is saying must happen. And do you guys, if y equals e to the 2x, and now we know that that's not really the full solution, but let's just start with this. If y equals e to the 2x, y prime, of course, would be 2x, y double prime would be, sure enough, y double prime is 4 times the original function. Why wouldn't sine or cosine work? Like sine 2x.
You have the negative and you take the derivative.
I like it. So what would be the equation? What would be one change I could make that would allow for the answer to be sine, cosine kind of stuff? You don't want to bring absolute values in, especially not if you're thinking about absolute value around this thing. Yes?
Hyperbolic sine of 2x?
No. I appreciate that, though. But let's stay with good old normal sine and cosine. Right? Sedated. They're not hyper in any way. Well, let's see. What's just start with y equals sine x. What's the y prime? Cosine x. And what's y double prime? So right there, you can set up an equation. Can't you? Y double prime equals, what would be here? Negative y. See, that's how you can create a diffie-q, right? Again, that's not from observations of the real world, which is really what you'd eventually use, what you learn in here to look at. But this is still useful. You're playing around with shit. You're seeing how equations can come together. You're seeing relationships between things. So how would I change this to make the answer sine 2x, cosine 2x? Just put a negative there. Yes?
Why would you not use absolute values?
And how do you mean use absolute value? Where?
Just like put it over the whole.
That would be for one.
Put it around what exactly? Sorry? Put it around the sign itself?
Yeah, like both terms on both sides of the.
You guys have to know by now that, I got to tell you, absolute value is actually, this is so weird for me to say, and it's recently that I've come to this decision, but I hate absolute value. It's the most devious function. It's not even a real function. It's composed of two. It's a piecewise hiding. Do you guys remember that? Absolute value of x is what? I always trip on my algebra students. They're like, well, it's x. No, because x could be negative, and then
Plus or
mind
minus
blows,
x.
right? So what, absolute value of x is x and negative x, depending on what the hell the input is. So it's a piecewise function. The minute you put an absolute value around any almost any function, you've created a piecewise situation. And derivatives of piecewise aren't difficult, but they are harder than they really should be, right? I like it. So then you get something that's not generally true across the whole interval, negative infinity to infinity. You could maybe restrict the interval. That's going to be part of what we talk about. But wow, it's going a long way to try to get something to fit. So I could actually, I mean, I'm not going to do this right now, but on your own, you could try to put absolute value there. Be really careful about how you work out the derivatives and see if it would actually work. Yeah. So obviously, if I did make this negative 4y there, now this hopefully I want to show something where I love this first night, because we're going to talk a lot about a lot of things that eventually we're going to get into officially and talk deeper about. But how many answers were there to my y prime one earlier? There was no. The y prime equals y. No. All right, let me ask this again. I'm sorry. How many families of answers were there? One. And this is a one parameter family, right? We're a one parameter family. How many answers do you think it's going to be to this? How many families of answers? 2. Kind of makes sense. It's a secondary. It's sort of like the fundamental theorem of algebra. There's an equal number of answers as to your degree of your polynomial. It's kind of nifty. Well, let's see now. So what would the answers be? Obviously, we just did. We know it's sine, but it's also cosine, because they both have the same kind of relationship with their derivatives, right? So let me see if you guys can see this. The answer would be y equals c1 sine 2x plus c2 cosine 2x. Let's see. You guys are looking like you don't believe me. Take the second derivative of this. Do it.
First times the second plus times the first.
There should be more writing. So, I mean, of course, when you take the first derivative, the sine piece stays positive. Pick up a 2 out there. But the cosine piece becomes negative. Get another sign. Becomes cosine. This one becomes sine. Don't forget your C2. And then when you take the next derivative, that stays negative, that becomes negative. The whole thing is the negative, and of course that's going to be 4 out there now, right? So this is now negative 4c1 sine minus 4c2 cosine, which is negative 4 times the original function, right? You guys cool with that? You guys see that? So you come into this class knowing that E has kind of like a period of 1. It kind of like comes back on itself once. Sine and cosine take 2 derivatives, kind of like come back, and then they're negative of what they used to be. I mean, that's, you kind of come in knowing that, but this describes that relationship in a equation. So that's, you know, this is a by observation I can see what the answer is. Will I always be able to see it by observation? No, because right now we're at x minus 2 equals 6 level, right? That's what this is relative to algebra. And of course, the minute we start adding in some distribution and shit, nah, crap, I got more stuff. I can't just do it by observation. And then we start adding in higher degrees, like, oh shit, I got to develop whole new methods. That's basically the progression we're going to take. Okay. One thing over here, I'm not really done with this, by the way. I got kind of sidetracked. Is that the only family? In fact, what's this family of answers? So this worked, right? Mm-hmm. Okay, so that's C1, e to the 2x. What's the other family of answers that might work here? Yeah, y2 equals C2 e to the negative 2x. Because one derivative, it'll be negative 2. Another derivative is going to be positive 4. So it is going to be 4 times the original. And again, why does it make sense that I had 2 families of answers? Because it was a second derivative. It's what we call a second order differential equation. I like it. There's some nifty connections you can make with algebra. Okay. All right. Oh, let's see. With any more little... Oh. So let me show you the first level of stepping away from x minus 2 equals 6 and getting into where there's a little bit more in there. But it's still doable. And it's like math 180 level. But not at first. Let's see if you guys can piece this together. What have I had? Now, what's been easy so far is there's no explicit x written anywhere. There's understood with respect to x happening here twice in this case. But what have I put down here? Which one do you want to use, Jeff? Yeah. Some of you guys might be able to figure this out by observation. But you can immediately tell this is another level of this. In fact, I don't have to do too much to this to make it so that it's almost impossible for you to figure it out by observation, but it's actually easy to just attack directly. If I rewrite this symbol, you could figure out a method. Of course, what's another way to write y prime? dy dx. Can anyone see a method? This is not too far away from 180. Sorry? Somebody's saying something. Integrals? Yes, yes. How would I do that? I can't integrate dy only with y shape, right? Think about it. Yes? Yeah, so if I multiply the dx up and divide the y down. Now, you've done this kind of thing before. When you do by parts, you have to figure out what dv is, and they have to integrate both sides to figure out what v is. You've done this kind of thing before. This is one step away from a total derivative kind of statement, and now what can I do to both sides? Integrate. I had to relearn this last time, but what is this? ln of what? It's trying to be a y. I'm sorry. ln, now say what you were trying to say earlier. Absolute value. Do you guys remember why this got to be there?
Because ln's only a positive function.
No, it has nothing to do with it can't be 0. What's the domain of this 1 over y? Everything except 0. If I don't put the absolute value, what's the domain of the resultant function?
Y is greater.
Strictly greater than 0. They don't match. You have to put the absolute value to make them match. Now, you can't integrate across anywhere where the inside function is discontinuous. Are you with me? And very often we forget this has to go there because we're integrating across positive numbers. But if you're integrating across the negative side of things, you have to have this here. Does that make sense? And it's not your fault. Teachers very often don't do a good enough job of making sure this shows up enough in earlier classes when you're like, oh shit, this is really the real answer. And of course on that side, whew, okay. And now what comes into play? Hey, this is 180 plus c. 11. So every now and again, and this method, I'm getting a little ahead of myself, and I don't give a shit, because this method is 180. So I could teach it to you on the first day, which is basically what today, really, because we're getting into new shit finally. This is called, not surprisingly, it's called separable. I can separate the y stuff and the x stuff. So almost any time you can do that, you do it. Unless doing that creates an integral that's either really, really hard or impossible, and then you try to come up with some other way. Does that make sense? So separable sounds like it's always the best way. 95% of the time. Now, I'm not really done. I should be able to get an explicit function here. Y is a function of x. And in fact, if I'm really nice, then I tell you that, let's just say y is greater than 0, I can take this away so there's no ambiguity. All right, if I say this. So yeah, this would be y equals e to the x squared. Are you ready? Plus c, but there's a better way to do this shit. Yes, because this is e to the x squared. Now be careful. This is where you got to get really used to being careful. Let me pull it up here so I don't get too low down here. This dude is going, right?
Yeah.
All right. He takes a little union break sometimes, so you got to tell me if he stops. They have a really good union. Okay. This is, of course, this. Right? Because then I would add power, so that's where it would. And what is e to the c? It is not c. It's c1. Why not? So very often what we'll do is we'll call the first c we use c1. So now I can say y equals c2. E to the x squared. You guys with me? Is that? Okay. And again, this is stuff, like I said, I'm just giving you like a surface view right now because there's a whole section devoted to separable equations. And we're going to get a lot deeper into this shit later. But I want to give you the idea how 180 does come directly into this class, but then we're going to leave it behind for a lot of what we do. Okay. Any questions so far? Any? You guys all right? Yes?
Why'd you go to C2 there?
Oh, so I made it C1, so the progression is that. You start off with C1, and the minute you do something to it, you can replace that with C2, because e to the C1 is a new constant, C2. And this, again, I'm trying to get you into this habit now, because later we'll be trying to match things up, and if you're not careful with your constants, they're never going to match up correctly. So you got to keep real good track. Don't just put C's everywhere. E to the C is not equal to C, except in extreme cases. So, I mean, yeah. Okay, I like it. All right, and you're like, yes, you're one of the future. Okay. Oh yeah. I wanted to throw this one at you. So this was kind of like an algebra equation where you have to do some distribution and stuff. You guys with me? We had to do a little bit of work to reorganize, and then we're able to attack it. So it's that kind of next level of equation solving. Now, I just want to throw this one at you. This is one there's no way in hell we're going to be able to solve this tonight because there's a lot between this and here and now. I just got to show you where we're working towards because so far this is like, what's the big deal with this class? Well, it's the second night. So what about... Now, of course, there's a method that you can create, and it becomes kind of a recipe. And that's a nice thing about DiffQ is it's all about what form is it in, what's the correct process, right? But so that's almost, huh?
I got it.
What is it?
It would be a destructive method, wouldn't it? The destroyer method?
Okay, well, annihilator method. You could use that method. Sure.
No, because it's X and Y. I don't think it's separable. It would have to. Well, I guess that is separable. Yeah, you're right.
So Cauchy Euler.
I'm good.
Okay. It's not separable. Trust me. Good Lord. You guys see it? It's definitely not separable. I mean, we're dealing with second order derivatives and dividing, and oh my God, it's not separable. They're all mixed really well together. This is something that towards the end of this class will become really easy, believe it or not. We just don't know what the hell the steps are. That's all, right? Okay, I like it. Yeah, so in my notes I just put, oh my God. I mean, that would be the reaction I would have to that. It feels like it should be a nice, easy answer, but my God, do you see how these have coefficients? So that's interesting in its own right. It's equal to sine x, but y can't just be sine x. I mean, because then you get a lot of mixtures of x and x squared. Do you guys see what I'm saying? There is an answer to this, but it's not obvious. You definitely can't do it by observation. You definitely can't do it by attacking it with the things you know already. And thank God, I mean, that's why the class exists. Thank God there's a reason for this class to exist. We have to develop the methods. I like it. Okay. Okay. All right. So I didn't want to fall into the trap of making things seem like there's nothing really new we're going to learn. There's some new shit we're going to learn. It's sort of like, again, it's sort of like taking that step to quadratic. You got to learn you got to learn how to factor, which might be brand new. You guys kind of, so we're going to learn things to get to the point where we can attack this thing. Okay. Oh yeah, I did want to. Here, before I leave these examples, real quick. So this guy was e to the 2x and e to the negative 2x, right? So what if I did this?
E to 2x plus 4.
Now, if that wasn't there, what's the trivial solution? No. Trivial solution. 0. Because that side is 0 for any constant, and that side is 0 when y is 0. Think about what I just said. When is that side 0? When y is negative 1. And what happens on that side if y is negative 1?
0.
It's 0, right? You guys with me? So the answer here would be c1 e to the 2x plus c2 e to the negative 2x minus 1. But this is interesting. So that's what we got earlier, isn't it? That makes it 0. That makes that work. And then that makes it work with that addition there. And again, you can check it out. If you take the derivative, you get 2c1 e to the 2x minus 2c2 e to the 2x. Y double prime equals, where'd I go? 4c1 e to the 2x plus 4c2 e to the 2x negative. So if I put that there, 4 times this cancels. That's plus 4. And that would be minus 4. So it balances. Do you guys see that? Okay, I like it. This is called, there's going to be 2 levels of this word I'm about to say. This is called either homogeneous or homogeneous, depending on if you think about milk or if you think about whatever. Homogeneous or homogeneous, it means that I have derivatives that are based off of y alone. Do you see that? The second derivative only cares about the value of y. So we're going to analyze these things and what the shapes would be. It's very interesting. If the derivative only cares about what y is, then it doesn't matter where you are in the x-axis, for example. So that'll come up later. And again, I'm doing sort of an overview thing. All right. I think that's enough of that. It's a little teaser for what the hell we're going to do later. Okay. So obviously if this would have been 8, this would have been 8, this would have been negative 2 to balance that out. Okay.
Why are you adding the 2 answers? Your y equals c1 blah 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 plus c2 blah, and not just have 2
So real quick,
separate?
let me take this out of the way for a second. That makes that work, right? That also makes that work. So the combination of them will still make it work.
Okay.
Yeah. In fact, to really put this in the form we normally use, those combine to be 0. So if that makes this equal 0 and that makes it equal to 0, then of course both of them will keep it equal to 0. So this is the idea of, this is like what we're going to eventually call YC. This is our complementary solution. And then the extra shit I throw at the end, those didn't have any C's in them, did they? They're the ones that balance out any other shit that's in there. So if I didn't make it equal 0, if it was this, so it's not equal to 0, well, the 0 answers still work because they'll let the other piece do its job. Now, of course, we're going to talk more about that later. If that didn't fully make sense, it's a little too early for me to say all that, but that was a really good question. So we're going to have a piece that's the YC that's related to making it 0, making that work. And then there's going to be a piece that makes the specific thing work. That's eventually going to be the full picture of an answer. All right, let's roll it way back and just talk about definitions for a little while. I just didn't want to jump right into definitions because it gets, it's a little tricky. Okay, I kind of gave away a little bit of what we're going to talk about. I think I've already used the word order. So this is a second order ordinary differential equation. Okay, so let's break that down. And in fact, to be honest, this is a second order linear ordinary differential equation. Good God. So there's 3 ideas we're going to tear down right now. We're going to break them up. There's the idea of order, which is really easy. And again, what was order all about? Yeah, just the highest derivative that I see is the order of the entire thing. Sort of like the degree of a polynomial is the highest power or highest degree of a term I see, right? So the highest derivative I see is the order of the differential equation. Then secondly we have, if it's, now this one's a little more direct, is it an ODE? Not ode to a Grecian urn, but ordinary differential equation. I can't believe that just came back from high school English. Ode to a Grecian urn. ODE and PDE. Anybody have any idea what kind of P would be in front of differential? Partial differential equation. Oh, shit. We're not going to study partial differential equations really directly at all, but there will be partial derivatives in this class every now and again. So, of course, normal derivatives look like this. What do partial derivatives look like? Curly D. I like it. What is the difference between the two, truly? Do you guys know? There's at least 2. There's multiple variables. Who knows how many? At least more than one, right? This is a true ratio of infinitesimal distances traveled. This is a true ratio, whereas this is not. That's why we have to use different symbols. It's really a nifty idea. That's the only reason there's different, because a student once had a really good question, why do we use different symbols? And I'm like, well, this is a true ratio of infinitesimals, which is a contested idea, but I don't care where you stand on it, they exist. And then this is not. Truly. Okay, that's all I'll say about that. So this is ordinary. This will be related to these guys, with d squared and d cubed and all that kind of stuff. This is partial. Partial y, partial squared y, all that kind of stuff. All right, so that's going to be pretty obvious. That's an easy classification to make. And then linearity is a little bit freakier, because it's not always easy to see what the independent and dependent variable is. Obviously here it's very easy to tell. What is the independent variable there? The independent variable is x, and the dependent variable is y, because of the way the ratio of the derivative is, right? So is this linear? It always means, is it linear in the dependent variable? Is it linear? Yes. The derivative expression itself is not being squared. That sounds weird, but I could have this happening. That would not be linear, because there's a y thing, a derivative of y, that's not linear. That's linear. That's linear. Who gives a shit? That's x. It can do whatever the hell it wants to. So if I put sine, if I put 4x squared, if I put sine of 4x squared, if I put sine of 4x squared divided by natural log of x minus 7, that doesn't affect the linearity. You guys still with me? So whatever the dependent variable is, all of its pieces have to be linear.
Okay, I think you just answered my question. I would say there's still dy dx, but the y was squared.
Yes. So this is linear, check. This is not linear, no. If I had this, but I had y squared, no. Because there's a y piece that's not linear. I like it. Now, let me show you an example where it's not easy to tell. And this is kind of an evil problem, but, you know, at this level, you should be ready for that. This one's kind of a neat one because what's the dependent variable? I don't know yet. Depends on how I want to rewrite it. So either you have to be told which one is supposed to be, or it really is not determined. And we should all be used to that idea that very often you can find inverse functions, not all the time, but still, if you have y's function x, you can sometimes find x as a function of y. You know. So here, if I just divide by dy, all of a sudden I got x is the dependent variable. Right? And to be honest, there shouldn't be y over here. That messes things up a bit. That's a little better. So if I divide by dy, I've got x as the dependent variable. Would it be linear? If I divide by dy, yes, because now if x is the dependent variable, it's fine. Now if I divided by dx, is it linear in y? No, because that's not linear. So in this kind of question, I ask you to investigate both, you know, linearity in x and y. Which one, or both, or neither? Because it depends on how you decide to rewrite it. I like it. I like it. And this is, can you guys see, is this separable? Let me write it again. Is this separable? Could you separate them? Yeah, you subtract, divide by 5y squared, divide by 4x, right? It's separable. I like it. But I don't want to say that. Anyway, that's all I want to say about that. I was going to say more, but that's too early. Okay. Just want to give you that example because it's going to come up every now and again. That's the one that's indeterminate unless they give you more in the question. Do you want me to check out all possible linearities? Or are you telling me it's x is the dependent variable? You got to tell me something. And then... Oh.
Sorry, this might be kind of dumb, but how is linearity, like how does that relate to all of this? Like how does, like, I don't want to say like how is it important, but how is it important?
So it's the idea of if it's linear, it should inherently have easier general methods of solution.
Okay.
Just like a linear function of x is easier to solve. You know, the minute you made it quadratic, so it's not linear anymore, much more difficult general methods, right? Mm-hmm. Still not hard, but more difficult than if it wasn't, right? This especially gets freaky and disgusting, right? Possibly, especially if there's more shit linear. Linear first order is like pleased your God. That's nice. Right? That's going to be generally the easiest ones. Doesn't mean I can't make it impossible to solve one, but generally they're easy. Linear second order, better than not linear second order, but worse than linear first order. That should make sense. You kind of with me? But if it's linear second order, easier methods. Not linear second order, more difficult general methods that I have to use. Yeah. Is that? Okay. No? Yes? Yes?
What would you probably answer that? You would say the first one, it is linear because the dx is...
So the way to answer, if I said check the linearity of x and y,
Okay.
you would say it's linear in x because if I solve for dx dy, all the x terms are linear.
Okay.
Not linear in y because if I solve for dy dx, there's a y piece that's not linear. Yeah. So it really does depend on the way you set up the d something, right? It depends on which way you decide to do that. Yeah. Okay.
So, sorry. Can you like manipulate your function or whatever to make what you want linear and then solve it that way?
Beautiful. Right? So if I had the option, no, this one is separable. So I mean, I would just do separable. It doesn't even matter if it's linear at that point because I can just use integral rules for this. At that point, this is power. The integrals go, I got you. Right? In general, yeah. If very often, if you consider x or y to be the dependent variable, one way will be easier, one way might be impossible. So yeah, that totally could change how you approach the problem. Okay, I like it. Okay. So let me do this. I think I want to shut up for a little while, let you guys do something. I do apologize for this. There were phantom lines that didn't show up until I printed them out, so just deal with that. This first side, section 1.1, if you guys could work on that. If you want to look at the back, you can do most of this, but there's part of this you can't do yet.